Good morning, everybody. Thank you for coming this morning. We have a nice plenary waiting for us. It's a pleasure for me to introduce Professor Benoit Fiorina. Benoit got his PhD in 2004 with a joint program between École Centrale de Paris and Research Center ENGIE. He then went to Stanford University for a few years as a postdoc, and he came back to France at the laboratory de la Centrale Supélec at the University of Paris-Saclay, where he is now full professor. Since 2018, he's also deputy director of the Mechanical and Energy Sciences, Material and Geosciences Doctoral School at University of Paris-Saclay. And he is also co-leader of the Combustion group at the M2C laboratory. He served as the chair of the French section of the Combustion Institute from 2015 to 2019, and is now a fellow of the Combustion Institute since 2022. And in 2020, received the Research Excellence Award of the Combustion Institute. His work is mainly focused on turbulent combustion modeling, and today we talk about the use of chemical kinetic model in complex simulations. It's a subject that reminds me of the old days as a PhD at UIC when I was moving my first steps into the combustion field, and I was looking with a little bit of terror to these giant models with tens of thousands of reactions and species. And the question is always the same: how can we deal with the need of having a correct description of the reality of the chemistry and the computational capability that we have? I hope that the talk of today will give us some tips on the recent advances in the field. So a warm welcome to Benoit.
Thank you. Thank you, Andrea, for the very nice introduction. I would like also to thank the organizing committee for inviting me today. I'm very honored. I will also first start by thanking all the contributors of this talk. So it includes my former PhD student who participate, who give me materials where I pick up some materials, but also my EM2C colleagues, such as Nasser, who is just sitting here. And also I would like to thank some worldwide colleagues with who I interact to prepare this presentation and who kindly give me some materials. So the first question is, where do we need combustion today? So if you have a quick look on where do we need combustion, we use combustion in transport, power plants, and industrial processes. If we have a look on the world primary energy consumption, and if you look at what is the primary source of combustion, it's oil, followed by coal, followed by natural gas and biofuel. All of these are burned. Okay, basically you burn this. And if you sum it up, you will figure out that combustion is about 80% of the primary energy conversion. And it's also responsible of 80% of the CO2, anthropogenic CO2 emission. Okay, so now the question is, how do we meet the Paris Agreement on Climate from that point of view, from that statement? So, question, can we do without combustion? If you look at the thermochemical engine, it's clear that they tend to disappear for small vehicles in Europe. Okay, all new cars sold in Europe must have zero CO2 emission in 2035. So it's clear that it's the death of ICE engine for small cars. However, ICE may still be a solution for heavy-duty vehicles and also both. Regarding power plants, there are no more oil-fired power plants in France. Okay, they intend to disappear in Europe. Regarding coal power plants, it's a bit more complex because it depends on the energy policy of each country in Europe. But apparently, half of them should close before 2030. So future won't be coal, fortunately. Gas turbine, however, remain interesting. Okay, to deal with intermittency issue of renewable energy. Now, maybe less known, industrial processes. Industrial processes represent 15% of the greenhouse gas emission, and many industrial sectors, such as the steel, glass industry, aluminium require high temperature sources and that you cannot manage without a flame. So you need flame to produce glass. And finally, I will conclude with aircraft. Aircraft, the math is quickly done. 1 kilogram of kerosene represents, in terms of energetic density, 50 to 100 kilogram of batteries. So electrification will not replace combustion in aircraft in the short term. So it means that combustion won't disappear now, but we need to do something. Okay, we have to, it's our mission to decarbonize the flames. So if you look at the aircraft example, this is a roadmap of the aircraft industry, at least Airbus. The idea is to put hydrogen at the center of the propulsion device. So hydrogen can be synthesized from H2O and, let's say, green electricity. If you can succeed to extract CO2 from the atmosphere, you can also combine CO2 and H2, and by using some power, well-known power to liquid route, it's possible to synthesize sustainable aviation fuel. You can also directly synthesize sustainable aviation fuel from biomass. Sustainable aviation fuel has a composition that is very close to the kerosene. At least can be done like that. So it means that it can be used as a drop-in fuel. And at the end of last year, in 2021, the first aircraft fueled by 100% of SAF flew. Okay, so you keep the same challenge than before, but almost. It's much more challenging. Another option that is much more challenging is to directly burn H2 in the combustor aircraft. Here, in addition to the storage issues and so on, in terms of combustion, you need to redesign entirely the combustion chamber. Okay, so it's a big challenge. Now it's interesting to see what will be the impact of this change in terms of CO2 emission. So this graph is extracted from a think tank work. It's called the SHIFT project. It's led by Jean-Marc Jancovici. And they do a study in France and they try to predict the scenario of CO2 emission depending of the actions. So the black line here is a target that you must satisfy in order to stay below the 2 degrees Celsius of global warming. It is assumed that there is an air traffic growth of 4% in 2024. Okay, and you see here that the dump here is due to the COVID crisis. Okay, no more planes. If you don't do anything, no technological change, then okay, you explode the limit. If you do some small efficiency gain, basically you improve the air traffic management systems, then you can save a bit of kerosene and you decrease the CO2. If you do some high efficiency gain, so strong technology change, and if you speed up the fleet renewal to make it every 15 years, then you are able to reach this target. Now, if you introduce sustainable aviation fuel and the hydrogen gradually, then you can pass below that limit here. Okay, so decarbonized combustion is required, okay, to meet this climate agreement. Well, this is what is not totally true, is that if you plot now the cumulative CO2 emission, you're not good enough because it takes too long to pass below this limit. So it means that it won't be sufficient. The combustion decarbonized flame will not save the world. We also need to take less the plane. Okay, that's what he's saying, is that to pass below this limit in 2050, the air traffic growth must stick to 0.7%. Okay, even not decreasing, but not moving to 4%. Okay, what are the main decarbonized fuel? Main decarbonized fuel are hydrogen, synthetic fuel from green electricity, all kind of e-fuel, ammonia. Okay, it's quite also interesting, better because it has a better volumetric energy than H2. Biomass, biofuel, such as bioethanol and so on. All of these are CO2 neutral. Okay, so they don't produce CO2. However, pollutants are still emitted. Okay, so are still unwanted species such as unborn hydrocarbons, soot, carbon monoxide, and also sulfur oxide and mainly nitrogen oxide. The problem with these species is that they are dangerous in small quantities and dangerous for health and climate. So there is a challenge now for combustion engineers. What they need to do is to design low combustion chamber for decarbonized fuel. So how to burn this new fuel, okay, by keeping low pollutant emission. The main strategies is to control the temperature, okay, to decrease the temperature. This is well known that if you decrease the temperature, you reduce the NOx production. However, the problem is that if you're going to be too low in temperature, you will not burn correctly. Okay, you will not burn correctly everything, and you may produce CO. And you can also promote some quenching issues, and this will lead to instabilities problem. So the big challenge of designing future combustion chamber is here. You must ensure the flame stabilization, but still by minimizing the flame, the pollutant formation. So it means that you need to optimize the geometry, optimize the combustion chambers, injection system, and also maybe to find new and innovative solutions to stabilize low temperature flames. So for that, you need advanced modeling for combustion engineer. Okay, this is our job to do that. There are a couple of reviews here that I just mentioned here that will discuss this in detail. To summarize, let's talk now about the physical challenge. Physical challenge for high combustion regime are not so high. Why? Because in terms of turbulent and chemistry interaction, because turbulent chemistry and timescale are quite disconnected to the flame chemistry. Okay, under high temperature condition, chemistry is very active and it's very fast. So the interaction between flame and chemistry is quite limited, and the old-fashioned model, okay, works quite well. For instance, if you do some infinitely fast chemistry assumption, you will have a very good prediction of a turbulent non-premix flame. If you move to, if you use a global step mechanism that is fit to retrieve when flame speed, then you will have a correct prediction of the flame stabilization for a premix flame. Start to be more complicated when you move to low temperature flame. Why? Because the chemistry is less intense, and you will broaden the range of interaction between the chemical species and the turbulence. Okay, so you will enhance this flame chemistry interaction, and it makes things more complex. So we need to account for interaction between detailed chemistry effects and turbulence. Okay, so this will be the this gives us the introduction of my talk, and the objective is today to discuss the modeling strategies for including detailed chemistry effects in turbulent flame simulations. So I will mainly have two parts. First, I will talk about simplified chemistry model, and then I will discuss the coupling of chemistry modeling with turbulent flow simulations. The complexity of a detailed chemical scheme is directly connected to the nature of the fuel that you are burning. If you consider H2, with 10 species and about 50 reactions, you are able to reproduce quite well the flame heat release and the flame speed. However, if you want to include the NOx formation, or if you want to burn ammonia, then about 30 species are needed, and you need to account for around 200 reactions, which is not so small anymore. If you move to methane, you need 100 of species. And if you want to consider kerosene or sustainable aviation fuel or biofuel, then at least 1,000 of species and several thousand of reactions will be needed. What is the problem? The problem is that now I want to connect this CFD, this detailed chemical scheme, with a CFD flow solver. I have to come up with a standard Navier-Stokes equation, okay, continuity, momentum, and the energy. Okay, and then I need to add one balance equation for each species involved in the detailed chemical scheme. So you have to end up with this set of balance equations. And here you have to face with two problems. First, there are too many equations. Okay, the number of questions is very high, so obviously it will be complex to solve. Secondly, it's not the only reason. Secondly, this chemical reaction rate, these guys on the right are very, very stiff. Why? Because there are radicals that are highly produced and highly consumed. This will cause very small time scale, okay, and a very short time scale, and also stiff gradient. And numerically, from a numerical point of view, okay, to capture this is very costly. So the challenge are to simplify this chemistry modeling, but still we want to predict some physical phenomena which are sensible to complex chemistry effects, such as the pollutant formation or extinction or ignition phenomena. So let's consider now a detailed chemical scheme made of N species. Okay, if we any thermochemical variables, such as the chemical reaction rates, can be expressed directly in a space called the chemical space. So it will be uniquely defined by Arrhenius law in this chemical space made of the pressure, temperature, and a vector of species mass fraction of dimension n. So it means that any chemical scheme will be defined, will have a given range of validity. Okay, so the range of validity of a detailed scheme covered a space or a subspace in a chemical space. The fact is that most of the, when you want to use a detailed chemical scheme to compute a practical application, the chemical space covered by a practical application is in general much smaller. Okay, you don't use all the space, the range of validity. So this detailed scheme is somehow oversized, okay, in comparison with what you need. So this is the idea of simplified chemistry model, is to find a dimension smaller than the number of species, to re-express this thermochemical state in a new chemical subspace. And the goal of the game, okay, is to find a simplified scheme whose range of validity somehow is as close as possible to the chemical space covered by a practical application. So from that, several methods has been developed by researchers to simplify the chemistry modeling. So there are mainly three main approaches. The first one is to reduce the chemistry. The second one is to tabulate the chemistry, and the last one is to optimize the chemistry. So I will discuss briefly all these methods. The oldest one, well, not the, we'll go back later, but one of the most famous one is the reduced chemistry. It's composed of two main steps. So you start from a detailed chemical scheme, and then the first step is to obtain a so-called skeletal mechanism. For that, you need to remove redundant species and reaction that will not affect some target flame properties. Okay, so this was initially done by hand, so it was a bit complex to apply it to large and very large mechanisms, but significant improvement have been done by by several authors, such as Turiani by the introduction of the sensibility method, and then Liu and Lo proposed the DRG method that has been extended to the DRG-EP method by Pepio Desjardins and Pitch. Okay. And then once you have this skeletal mechanism, you can go further proceed with the reduction by finding analytical relation between species. In general, you're doing that by assuming quasi-steady state. Again, some automatic method has been developed, such as the CSP or the level of interest method, importance method. If you find an analytical relation between two species, it's good because you don't need to transport anymore these two species. Only one balance equation is required. So you can save, again, CPU time. So now tools are mature enough. Okay, there are several tools that has been published. Tools are mature enough to automatize the reduction process. We can, for instance, see the Arcan code, okay, that is developed jointly between Cornell University and Fairfax. Okay, so a remark, it's important to note that both steps, okay, require reference data set. Okay, if you want to find which species are redundant or which species are at the quasi-steady state, you need to define some reference case to compute this term, and by doing so, you will somehow define a range of validity. I will show you an example. For that, I took the LU19 analytical mechanism developed by Liu and Lo. They start from a detailed GRI mechanism made of 53 species. They applied the DRG method to obtain 36 species, 222 reactions, and then they find an analytical relation between species by applying a quasi-steady state, by finding quasi-steady state species. Okay, so I will now compare the reference detailed chemical scheme with this analytical scheme, and there is a canonical but challenging case to check if a detailed scheme, reduced scheme is working, is to take simply two flames, one premix flame and one non-premix flame. And if you are able to capture with the same reduced scheme both flame configuration, you are doing a good job first. So if you do so with the analytical scheme. So here on this slide, I show on this slide, on the left, there is a laminar premix flame, solved with the 1D solver. On the right, a non-premix counterflow flame, solved also with a regate solver. And I compare here the CO mass fraction and the temperature. And you see an excellent agreement between the detailed scheme and the analytical scheme. Okay, so it works very well. So now I will introduce the other method. I will talk about tabulated chemistry. Tabulated chemistry, the idea is not only to reduce the number of species, but it's going a bit further. It's also re-express or project the thermochemical state in a new set of coordinates, which has a lower dimension, much more lower dimension. Okay, so in general, this set of coordinates are combination of state variables. So the objective is to tabulate the thermochemical state in a lookup table during a pre-processing step. And the key issues are how to identify this reduced subspace, how to build up the chemical table or the manifold. And sometimes you can have also some issues because the table is going to be too heavy and you may have some memory size issues. Tabulated chemistry is very efficient because the access space is confined to low dimensional manifold. This has been observed by Ulrich Maas and Dominique Thévenin. They did an interesting simulation. Here they compute, results are shown on the top. They compute a non-premixed flame, okay, non-premixed flame for different level of turbulence. So it's a laminar non-premixed flame on the top left. It's a weakly turbulent non-premixed flame on the middle, and it becomes highly turbulent on the right. So real-life solution are plotted on the top. Okay, this is physical space, X, Y solution, and projection into the chemical space are shown on the bottom. So these solutions are projected on a three-dimension axis made of three species. N2, H2O, and H. What you can observe is that there is an attractive space, okay, that is called a manifold. There is an attractive space, and you can also observe that the dimension of this attractive space tends to increase with the complexity of the problem. Okay, but there is a strong attractive space. Initially, Ulrich Maas and Steve Poe proposed a method, okay, to automatically identify this attractive space. It is the so-called ILDM method. They succeed to identify this space by computing the eigenspace decomposition of the Jacobian of the reaction rates. Okay, so this works very well if you want to capture in high temperature region of the flame. However, you start to have problem if you in low temperature flame because the chemical reaction competes with the molecular diffusion and the size of the attractive manifold becomes too large, or at least with LDM, it's difficult to compute. So an alternative that is used in many applications today is to compute directly the manifold from laminar flame elements. So this method is the flamelet, are called also flamelet-based tabulated chemistry method. So the idea is to identify a set of flame elements. So basically, initially, either you choose premix flamelets or non-premix flamelet or zero-D reactor, for instance. If you use non-premix flamelet, you are using a so-called flamelet model developed by Peters. If you use premix flamelet, these are the FPI or FGM technique. So a flamelet library is computed after selecting this flamelet. A flamelet library is computed in the physical space with a detailed chemical scheme. And then you need to make some empirical choice of manifold coordinates. Generally, coordinates that are chosen are the mixture fraction, the progress variable, the enthalpy. But this is completely empirical. Okay, so you have to do it a bit by hand. At the end, everything is mapped in a lookup table of NC dimension, where NC is the number of the manifold coordinate. You can then couple this manifold with a CFD solver by solving, in general, one balance equation for each manifold coordinate, and by picking into the chemical lookup table the thermochemical ingredients that are needed to perform the simulation. This is going to work as soon as the range of validity of the tabulated chemistry method is in agreement with the chemical space covered by the applications that you are targeting. If we go back to our previous example, we have compute we have compute a chemical lookup table made of premixed flame element. And if you use this chemical lookup table to compute made of premixed flame element, if you want to compute a premixed flame, there is no surprise, it works. Okay, it works very well. You see an excellent agreement between the two solutions. However, it's not going to work anymore if the chemical space covered by the practical application does not fit completely the range of validity of the tabulated chemistry model. If you do the same exercise than before, and if you applied this tabulated chemistry method made of premixed flamelet to a non-premixed flame, so we will see that the temperature is quite well reproduced. Okay, here it's quite okay for the temperature, but you completely mispredict the CO mass fraction. Okay, so there is another prediction of the CO prediction with the tabulated chemistry approach. So what to do? There are several solutions for that. The first solution is to compute multi-regime manifolds. So instead of first computing elements in the physical space and then projecting into manifold, it's possible, in fact, to directly write down balance equation of the manifold directly in the reduced coordinate space. So this is the redim reaction diffusion manifold approach developed initially by Bikoff and Mass. An alternative is also the multi-regime flamelet manifold, which are similar techniques. The fact is that when you write down this equation, there are some terms that appears, which are the gradient of the coordinate in the physical space. Okay, and these terms need to be modeled. How to model this term? You need to find in general to define a reference combustion element. So again, you need somehow some physical representative flamelet at the end to close this equation. However, it has been observed that this gradient estimate is less important as soon as the size of the manifold increases. Okay. So there is an alternative will be to include directly a wide range of different flame elements in the same manifold. Okay, I told you before that in general we either choose premixed flame or non-premixed flame or zero director to be tabulated in the same table. Here, the idea will be to try to tabulate all these terms in the same database. The problem is the empirical choice. Okay, it's not complex to compute these flame elements. We know how to do that, but the question is how to empirically choose the manifold coordinate. It's not going to be trivial anymore to find the right coordinate. Here, machine learning tools, okay, are quite interesting for that. For instance, if you look at the work from Alessandro Parente teams, they use machine learning to identify this technique, and in particular, they develop the local PCA, principal component analysis method, which is good because it can post-process an ensemble of data and find what are the best coordinates that reproduce most of the variance of the covariance of this data. While then you have to face with the second issue is that when you have many different data in the same to be tabulated, these data are not necessarily structured in the phase space. So you need to find also a solution to interpolate this data, and you can for that also use supervised nonlinear regression algorithm, such as neural network, artificial neural network, or Gaussian regression process. Okay, so these are the actual research on that topic. Okay, now I will move to the third approach, which is the optimized chemistry method. Actually, optimized chemistry is a very standard technique. Maybe it's the oldest way to couple to include detailed chemistry effect, basic chemistry effect into a CFD simulation. It's also the global empirical global step mechanism. So the idea is to select one or two reactions, a few species, and to optimize the reaction rate of the species to achieve some target flame properties. So I give you here two examples. There is a famous scheme from Westbrook and Dreyer, and on the right there is a scheme developed by Franzelli and Serfax teams for kerosene. If you apply this scheme, now if you go back to our canonical test, if you apply this global scheme to a premixed and non-premixed flame, it's quite okay for the temperature. Okay, prediction are not too bad. However, you are not able to predict the CO at all. Why? Because the CO that is present in this mechanism is just an artifact. Okay, it's an intermediate space, but it does not really represent the CO. It's just used to tune and to obtain the right flame speed. So this motivates us at EM2C to develop a new approach that is called the virtual chemistry. The idea is to build up a reduced chemical scheme from scratch, okay, and to use virtual species and virtual reaction whose chemical weight constant and thermochemical properties are optimized. So we first need to generate a learning database. So again, to generate this learning database, we can again select and pick up different flame elements such as premix flame, non-premix flame, zero-D reactors. And then we'll use a machine learning algorithm in order to train several independent schemes. So the first one is we first train a main virtual mechanism. Here I show you an example of a two-step main virtual mechanism. So I is a virtual intermediate species and pK is a set of virtual products. And to optimize the scheme is in order to capture the right temperature, the right heat release, and the density. And this is then directly coupled to a CFD flow solver. Then we developed several sub-mechanisms for CO mass fraction, for NOx, for soot. Okay, so we extend somehow the global step chemistry to be able to capture the pollutant predictions. So I show you here two short examples of virtual chemical scheme. On the top, you have a three-step virtual chemical scheme to capture the CO prediction. Here you see that each rate of progress is closed by a standard Arrhenius law, okay, and all the Arrhenius law parameters, such as the pre-exponential constant, the reaction order, or the energy of activation, are optimized by an in-house genetic algorithm to verify, to satisfy the learning database. We also developed a mechanism for NOx formation. Here we have a 6-step mechanism with 2 steps dedicated to capture the fast and the prompt NO, and the last 3 steps dedicated to predict the thermal NO production at the slowest time scale and also the reburning process. Now, the good thing with this scheme is that if you train the scheme to capture both premix and non-premix flame, okay, then you are able at the end to capture the chemical flame structure of both configurations. So we show here that it works quite well to predict the CO and the temperature in both premix and non-premix flame. These are some examples of laminar flame simulations that we have performed with the virtual scheme for CO on the left, NOx on the middle, and soot on the right. What is interesting is that the number of species that you keep at the end is always of the same order of magnitude. That does not really depend on the size of the initial mechanism. So in particular for soot, it's quite interesting because you move from a 300 species mechanism to a 12 species mechanism. Here you have 12 species to capture both soot and also the main scheme. Some efforts can also be done to accelerate the computational speed up. Okay, so this can be done here. Why? Because many CFD solver employs an operator splitting method for detailed chemistry flame simulation. So it means that most of the CPU time in a CFD flow solver, when you have a very large mechanism, most of the CPU time will be spent. Well, don't work, but will be spent on the source term computation. So effort made to speed up the computation cost of reaction rates is relevant. So many techniques has been developed, okay, to accelerate the computational source terms. For instance, we have the ISAT method, which consists in tabulating on the fly the chemical reaction rate during computations. There are some stiffness removal technique, adaptive chemistry, where the idea of adaptive chemistry is to use different reduced schemes depending on which region of the flame you are located. Okay, and finally the dynamic cell agglomeration. I will develop a bit more this one. The idea of dynamic cell agglomeration is to start from a grid, okay, that discretizes the flame. And instead of solving the chemical reaction rate on each point of the grid, which is very expensive, the idea is to cluster the flames that have the same thermochemical properties, and then to compute the chemical reaction rates only once in each cluster. Okay, so you save computational time, and then you can map back the solution to the individual sites. So several studies have been performed to develop this dynamic cell agglomeration. Here are some examples of the literature. But the key question, when you do that, the key question is how to define and to identify the similar thermochemical condition. Okay, how can you cluster the grid? PCA, principal comment analysis, is again a quite interesting tool for that. So this PCA method has been used. It leads to the PCA square method, which is a quite new method developed by Alberto Cucci, Grenda, and Heinz Pitch. They use PCA to dynamically identify the optimal set of relevant features, and they have applied it to simulate non-steady, non-premixed laminar flame, pulsated frame, and they compare here the full PCA on each slide with the PCA, the full detailed chemistry solution against this PCA square method, and you see a very good agreement, okay, for both fields. So it works quite well. The good thing with this method is that you can control the error by two ways: by playing with the explained variance, which actually is the number of principal components that you use at the end of your PCA to describe the main features, and the second parameter is the clustering tolerance, which is the discretization of the PC's dimension. They succeed to have a speed up of 410, okay, depending on the error. Okay, so now, we will stop a bit and try to analyze and compare all these reduced chemistry methods. So in all these methods, you can see some common point. Okay, and the common point is that the range of validity and the cost of reduced chemistry method are given by the nature of the data that you are used to simplify your chemistry. For skeletal mechanism, this is given by the target data that are used to remove redundant species and reaction, or then to apply quasi-steady state assumption. In tabulated chemistry method is simply given by the tabulated manifold, and in optimized chemistry method, it is given by the learning database. Range of validity and cost is also directly correlated to the dimension of the simplified chemistry method. Okay. At the end, for skeletal and arc mechanism, it will be given by the number of selected species. For tabulated chemistry method, it will be given by the dimension of the tabulated manifold. And for optimized chemistry method, it will be given by the number of virtual species and reactions that will that you will have at the end. If you want to rank them in terms and compare them in terms of practical use, cost of accuracy, definitely the cheapest method is the tabulated chemistry method. Okay, it's extremely efficient. You cannot do better on simple flame configuration. So if you want to compute a simple turbulent premix flame on a non-premix flame, it works very well. It is, however, less suitable to complex flame structure. You need to extend it, as I discussed, but it can be quite complex because the generation of high dimension manifold can become very sophisticated. And I don't think an engineer, well, a combustion engineer won't have maybe the time needed to build up by himself this manifold. So it can be a limitation of this technique. Skeletal and arc mechanism. The good thing is now there are many progress that have been done to automatize this method. So there are several codes that are standalone and that can automatically reduce the mechanism. However, it's still expensive. Okay, the number of species that is reduced is not high enough sometimes, and you still have to end up with many species. And also the stiffness of reaction rate is still a problem. Between them, you have the optimized chemistry method, which enables the prediction of the pollutant today, thanks to a machine learning algorithm. But still, I think we have some effort to do and some progress to do in the optimization algorithm. Okay, so now I will move to the third part, and we'll discuss the coupling of the chemistry with the turbulent flow simulation. Okay, so we have our detailed chemistry. We obtain the simplified chemistry model. Now the question is, okay, how can I put that in my CFD flow solver? So I will stick to turbulent flame simulation. So I have to choose either with RANS, or I can have a RANS on an LES approach. So again, there are three methods that exist to couple this a simplified chemistry or any chemistry model with a turbulent flame solver. Methods are based on geometrical assumption, statistical analysis, or there are mixing-based approach. We'll stick today to large eddy simulation because it's very interesting to capture unsteady phenomena, but some of what I will discuss is also valid for runs. Let's start with the geometrical analysis. Geometrical analysis, the idea is simply to assume that a flame can be described by a surface of a given thickness. So this works as soon as the flame is not, the scene reaction zone of the flame at least, is not disturbed by the turbulence. Okay? So geometrical approaches are quite well adapted to flamelet regime. You have to face with two issues when you want to apply a flamelet geometrical approach to a large eddy simulation. The first one, okay, that is, if this is your flame front, okay, and this is your grid side, the first one is that the flame thickness is, in most of practical application, is much smaller than the mesh size. So if you do nothing, you have numerical problem. So you need to do an artificial broadening of the flame front that is filtered. So there are different techniques. I will discuss them now. Second flame model and filtered flame front are the main approach. To explain what is the principle of flame thickening or artificial flame wrinkling, we can take again our canonical example, a laminar premix flame. I show you here a variable that is called the progress variable. It's a good candidate to describe a flame because it moves from 0 in the fresh gas and reach 1 in general in the burnt gases. And you can see here, okay, the transition between fresh gases and burnt gases. It represents the thermal layer, or it can be even the reaction zone. And here you can see that this reaction zone is not discretized. Okay, you have the grid size is larger than the thermal gradient. So if you want to plug this directly into a CFD flow solver, you will have numerical issues, and you will never recover the correct flame speed. Okay, so flame speed cannot be captured because you don't have enough grid points to measure the reaction rates. So you can do some flame thickening. So the idea is simply to multiply the molecular diffusion by a factor F, and at the same time to divide the chemical reaction rate by the same factor F. If you do so, at the end, you have a second progress variable. You obtain a second flame structure. And if you choose the correct factor F, you can have enough grid points in the flame front, across the flame front, to be able to transport and to propagate the flame at the right speed. You have to solve a balance equation for these filtered quantities, and this is the second flame model for large simulation, TFLES model. An alternative is to do some explicit flame filtering. So for that, you need to choose, instead of thickening, you filter. So you apply a Gaussian filter explicitly of a given size delta. And again, you can find the right flame filter size in order to be sure that your flame is well resolved on your LES grid. And you come up with another equation, which is an equation for the filtered progress variable or filtered species equation, which must be closed. Okay, and there are different techniques such as the F-tackle approach that you have developed to close this equation. This is the first problem, but that's not the only problem. The only problem is that some part of the flame wrinkling is not resolved also. Okay, so it means that the turbulent will affect the flame, it will wrinkle the flame, but even in large eddy simulation, we will not resolve the entire flame wrinkling. And some part is not resolved, and you need to provide a model for that. So the quantity that you want to model is a subgrid scale flame wrinkling, these things here. And it's defined as the ratio between the surface of the wrinkled flame versus the surface of the resolved flame. So different techniques have been developed. There are many models that have been developed to model the subgrid scale flame wrinkling, such as analytical model or dynamic formulation. I will pick up one of these models, which is commonly used. It's the Charlotte-Menvaux and Venant model, where you have here an expression, an analytical expression that is given for the subgrid scale flame wrinkling. So you see the physics, okay, on this term. So this equation look a fool, but anyway, you have here something interesting. You have a function of the turbulent subgrid scale, turbulent velocity. Okay, this is the fluctuation of the velocity. So in this, the fluctuation will cause the wrinkling of the flame. So it's an input of the model. You have also the thickness of the laminar flame that is involved. Okay, there are several parameters, the laminar flame speed that will play a role too. But there are also this parameter here, that is the beta parameter, which is completely empirical. Okay, so we don't know this parameter. And the problem is that this value of this parameter, it appears that it changes. It depends of the kind of flame that you are computing. It depends locally. It can also locally change within the same flame. So it's not universal. So effort have been done to identify this term. And for instance, dynamic closure have been developed. The idea is to use the result solution of the LES and to use a test filter in order to automatically identify and compute this term during a computation. So you don't have to tune it anymore. If you do, so this is an example of a simulation that has been performed again. So you have a turbulent premix flame simulation performed with a dynamic closure formulation. And this is the flame isosurface that is colored by the beta coefficient. And you can see that the beta coefficient is changing. Okay, so it's far from being constant. So it's important to use dynamic formulation if you want to be predictive. There is another possibility, which is quite recent, is to use the machine learning algorithm to model this subgrid scale flame wrinkling. So this is some work that has been performed by Serfax, by Thierry Poinceau team. They generate a learning database made of solution of a turbulent premix flame, and they use this learning database to train a neural network method in order to obtain a model for the subgrid scale flame wrinkling. Okay, so this is another way, recent way to estimate this term. The subgrid scale flame wrinkling will impact the turbulent flame speed, so it's important if you want to have the right flame power. Okay, because the turbulent flame speed is directly connected to that. But also we have observed that it has an impact, subgrid scale flame wrinkling has a strong impact on the pollutant formation. Okay, in particular, such as intermediate species such as the carbon monoxide. So it means that when you develop a turbulent combustion model, you should take care to include the impact of subgrid scale flame wrinkling in the prediction of pollutant. So here we show an example of simulation where we show that the wrinkling will enhance the CO formation. Okay, so other technique to couple a simplified chemistry with a turbulent flame simulation are the statistical approach. Statistical approach aims to decompose a mean or a filtered quantity by introducing a joint PDF. The key question is how to presume the shape of this PDF. So there are either presume shape PDF method. Most of the time, a beta function is assumed for the PDF. So it's cheap, okay, but it's not always very accurate. If you want to be much more accurate, you can move to transport PDF approach with either Lagrangian or Eulerian strategies. So finally, the last one is the mixing-based technique. Here, it's the opposite of the geometrical approach. You don't assume that the flame is the surface, but you assume that it is kind of a reactor. And within the reactor, the assumption is made that there are some fine structures that are reactive and some surrounding that is non-reactive. And you mix these two quantities in order to estimate the filtered reaction rate. So you end up with some terms that need to be modeled. Okay. And when you develop this mixing-based model, you have many terms to model. Okay, so you need closure for that. However, it has been shown that this is quite well adapted to distributed combustion regime, such as mild combustion, okay, where the temperature is very low. This is an example of DNS post-processing performed by Parente team, who shows that this EDC dissipation concept works quite well. Okay, so now we'll try to summarize what we have said. And if you look, we identify 3 ways to move from detailed chemistry to simplified chemistry, 3 ways to move to simplified chemistry to turbulent flame simulation. So there are many combinations, okay, that are possible, and a priori, all combinations are possible if you want to move to the detailed chemistry to the practical simulation. Everything in the matter of money, okay, so depends how many hours do you have, CPU hours you have in your pocket. So as we told, analytical you have optimized chemistry. You can do the same exercise for the turbulent modeling, okay? Turbulent flame modeling. So geometrical approach are in general cheap. Okay, why? Because just thickening a flame front does not cost anything, and estimating the subgrid scale flame wrinkling with an analytical addition also is not expensive. Statistic presumed PDF is also quite cheap. Mixing base model are a bit more expensive, and statistic transport PDF are quite expensive. Okay, if you combine two methods that are expensive, at the end it's very expensive. Okay, so this is an example of a very nice and accurate simulation that has been performed. A recent one. It's a turbulent premix flame in a swirl combustor that has been performed by combining a transport PDF method with an analytically reduced chemistry. This is an example of mild combustion chamber simulation with a mixing-based approach combined with a reduced chemistry. You can also combine reduced chemistry again with a geometrical approach. Okay, so this is cheaper because you don't have to transport any PTF, but still can be still expensive. This is a simulation obtained by Serfax Group on a spray burner. Can also combine tabulated chemistry, such as here the redim approach with a transport PDF. Okay, so it was the same cost than reduced chemistry with geometry approach. We can also have some optimized chemistry, for instance, with geometric approach. So here the accuracy decreased, but CPU cost also. And finally, tabulated chemistry and geometrical approach. It is the cheapest. Okay, what to do with that? What is the use of this technique? This is my point of view. Okay, I think that the most accurate method, and this is what we see today, is that they are limited to one shot. Okay, it's a good way of doing some small experiment on realistic configuration, but in order to understand the physics, in order to understand what's happening. But you can pay one simulation by using several millions of hours, maybe. So this is definitely never be used in a daily design process by a combustion engineer. That's why the most reduced chemistry method, which are less accurate but can still be improved, are interesting, I think, for the daily design of industrial burner by combustion engineer. I will give a few words. I'm concluding just for a few slides, one or two slides. A few words about the hot challenge, okay, that remains for turbulent combustion modeling of decarbonized flame. If you look at turbulent, so there are some specific issues dedicated to each fuels now that we have to tackle. For instance, for H2 flames, it seems that the differential diffusion phenomena in turbulent flame is very important. Recent study from Berger, Attili, and Pitch shows that the thermodiffusive instabilities will affect strongly the turbulent flame speed. Also, you have a wide range of NOx to capture. Ammonia is complex because you need to find a way to stabilize the ammonia flame, and also it may produce NOx. And turbulent for SAF, you have to deal with two-phase flow flames and soot formation. So we may need to design new combustion chamber also with new stabilization process. This is an example of a plasma-assisted combustion technique. Okay, maybe this is interesting to stabilize future non-carbonized flame. And I would like also to conclude by some remarks about the role of machine learning in combustion modeling. As I tried to show you during this presentation, machine learning appears sometimes. And today it has been used, I think, by the researcher to reinforce the classical modeling routes. Okay, you can see that it has been used to identify the best manifold coordinates, improve the subgrid scale flame wrinkling, optimize some chemical scheme, improve some optimized chemical scheme method, or also to find a point with similar thermochemical property. So it does not yet revolutionize the way we are doing, or I don't know why. Maybe we are too stick to our habits or not. I don't know. But this is how it works today. But it's an open question. Okay, maybe it will change later. We'll see. Thank you for your attention.
So thank you very much, Benoit. I don't know, we have some time for the questions. I just need to remind you before I forget that after the talk, we have a picture. So we will meet downstairs to take a picture of all of us. Any question?
So there is one more method, like, I don't know if I missed the initial slides. So the chemical reactor network modeling, like you simulate CFD with this like very reduced mechanism, and then generate a chemical reactor network and solve with the detailed chemistry for basically for the emission estimations. So how do you place that kind of a technique along with these?
I would have placed it more with a mixing-based approach, but
Okay.
For me, it's kind of a Ragnar network. It's kind of a mixing-based approach because you model by perfectly steered reactor or C reactors. You decompose your simulation.
Okay, and just one more question, like when it comes to multi-fuel, for example, natural gas with hydrogen or blended fuel, and have you done any of these study for those blended fuels, like which chemistry or which method may be more suitable or something like that?
It depends. The most difficult in terms of turbulent combustion modeling, I don't think using a blending fuel is in general not more difficult. Maybe it's more difficult for the chemist because the chemistry is maybe more complex. But in terms of reduction, is not maybe the more complex. What is very complex, however, is to have different injection. If you want to compute, let's say, an industrial burner, okay, with an injection of methane that is separated to the injection of hydrogen, this is complex in terms of turbulent combustion modeling because you need to increase the dimension of your manifold.
So, sorry, my question was more related to like emission estimations from the blended fuel mixture, like for example, the lean conditions for the premix cases. And that's where I find there are some challenges to estimate NOx and CO especially.
Okay, you mean in terms of chemistry reduction?
Maybe.
Okay, yeah, it's interesting. Something you should look at.
Thank you, Benoit, for the super interesting talk. Josué Melguizo from L'Institut Peprim. My question is, when you do all these fittings with like 1D laminar flames, premixed, non-premixed, like what happens with these mechanisms when you go towards limiting conditions like quenching and critical strain rates and all these things? So they continue to perform well? And then the other question is more on the detonation side of things, which I'm interested in adding more chemistry to detonation modeling. What would you suggest? So detonations are driven by autoignition. Is there some lower dimensional manifold that one can think of that would capture all the potential thermodynamic states for ignition, for instance? It's just I want to hear your view on this because I'm interested. Thanks.
Just let me remind the first question. I forgot. The first question was
limiting behaviors, quenching,
limiting behavior.
strain rates, all that.
Okay, well, if you move to quenching, the difficulties is that it's more complex from a chemical point of view because it appears at low temperature. It's more sensitive, and in general, you need to increase. What you have observed is that you need to increase the dimension of your reduced chemistry. So basically, whatever it is, optimized chemistry or tabulated chemistry, you need to add dimension in order to be able to accurately capture that. So we have shown that. For instance, the optimized two-step mechanism that I show works quite well to capture this quenching, but with one step, you are not able to capture it at all. Okay, and so we can expect that with 3 steps, it will be better and so on. And secondly, yes, definitely to capture the detonation phenomena, I would make the effort on capturing the autoignition delay time in order to have the right structure after the shock. And for that, we can include the basic thing is to include autoignition events in your training database that you use either for tabulating the chemistry or for optimizing the scheme. But it's possible. We have also done that. The virtual optimized chemistry scheme, we have developed, we have optimized it against auto ignition. So this is something. It depends also if you care about the species, if you just want the temperature, or if you also want to look at the pollutants or not.
Thank you for the talk, very nice and clear. And my name is Franco Marra from National Research Council. In the several approaches you suggested for reduce the computational costs, it seems to me that you have not mentioned the possibility to adapt the mesh to the flame and not the flame to the mesh. So I mean algebraic mesh refinement. There is some specific reason why you not consider this possibility?
No, I think no. Of course, you're right. I didn't mention it because it's more it's interesting. But the problem, I just talked with some people who are doing that, and what they say is that the problem that they are, if you want to do detailed chemistry, if you start to refine the mesh, at the end you have to come up. We have the stiffness of the reaction rate, which is still an issue, and you have some CFL restriction. And at the end, you have to slow down also the computational time step. So you may not solve all the issues with this adaptive mesh refinement. It will be more accurate, but I'm not sure it will be cheaper in terms of CPU time. Okay, because you have to face with these radicals anymore. But maybe it can be combined with another stiffness removal approach or technique. Things are.
So you give a nice overview of many techniques in the past, and clearly in the last 10-15 years, with all of the advancements in computational sciences, data analytics have really led to a lot of the advancements you showed. But in your opinion, what's the prospect for the future? Like where is the field, the techniques, the opportunities, the gaps are that are going to drive the next advancements? For example, in the accuracy to cost plot, there's a positive, all techniques are on a positive slope, on a right running line. What's the prospect to turn that one on the other way around?
I don't want to be in trouble with colleagues. That's why I put a straight slopes. But no, I know it was just a simplified view, of course. It's maybe not straight. Well, I think the challenge are we should identify. Well, also I didn't mention that one challenge will be also reduce order modeling. Okay, I didn't mention it, but I don't think that the future for combustion engineer will be a super expensive LES and even LES. So we may have still to move to even lower CPU approach with very low order modeling. So one key issue is maybe to move back to this low order reduced modeling, maybe to define them and to develop them by using LES. So there are probably some more to do with that. And then there are some new physical phenomena. So that's with hydrogen, they come back. With ammonia also, ammonia is going to be very challenging in order to be able to compute this, to predict all the NOx formation at a very low temperature, so with strong interaction with the turbulence. We also need to extend our turbulent combustion model in order to be, usually the method, as I said, are either based on geometrical approach, either based on distributed regime, but sometimes you have both configuration. You may have strong interaction in a flamelet regime for the temperature, but some species that are slower can react in a distributed reaction regime. So maybe the challenge are to be able to evolve our turbulent combustion model to capture this multi-scale phenomena. So things are still such kind of example.
I'm really sorry I got called. We have to go. It was a very interesting talk and discussion. We can continue later, maybe, with Benoit. So we meet downstairs for the picture before the sessions.
Me too. This is a great guy. It was very nice and very combative. Also, you have to face very strong problems during security. You have some He's not working here. Okay, thank you. Thank you.